video, we're going to define what divergence is. So if f is p of x, y, z, q of x, y, z, r of x, y, z. So basically f is a vector field in 3 space. In the last video, I think I named the component functions f, g, and h. I kind of prefer that to p, q, and r, but this is what your book uses, so I'll try to remember to be consistent with those. These are just the component functions, not to be confused with points. Okay, this is a function of x, y, and z that gives me the first component of f. Okay. The divergence of f is defined to be this del operator dotted with f. So curl was the del operator crossed with f. This is the del operator dotted with f. So that would be partial with respect to x, partial with respect to y, partial with respect to z, dotted with the functions p, q, well, the vector field p, q, r, whose component functions are p, q, and r. And, of course, we replace multiplication when I'm combining an operator and a function with just applying that operator to that function. So I'm going to get the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. It's a sum of these functions. Remember, the dot product does not give me a vector. The dot product, if I had numbers here, the dot product would give me a number. What this gives me here is a real valued function. So curl is a vector valued function. It's actually a vector field in its own right. This is a real valued function that I can associate with a vector field in 3 space. One quick note. We said this del operator means this, so it's just defined in 3 space. Some textbooks will still call that the del operator and do these things in 2 space. Our textbook doesn't. The one time in 2 space where we've seen that symbol is when we take the gradient of a real valued function of 2 variables. We do still use that symbol for the gradient, but we would not consider it the del operator applied to that real valued function. We're just using the same symbol. The del operator does put us in 3 space as it's defined in your textbook, but textbooks do vary on their definitions. Okay, so let's just practice taking divergence of a real valued function. Sorry, not of a real valued function. We can't do that. Of a vector field. Okay. So let's suppose that we have f of x, y, z is the vector field e to the x times cosine of y, z, comma, x, y, z squared, comma, y over x, z. Okay, so if I want to take the divergence of f, that's del dotted with f, so I'm taking these operators, the partials with respect to x, y, and z, and I'm applying them to this vector field, e to the x cosine of yz, xyz squared, y over xz. So I'm going to get the partial with respect to x of e to the x times cosine of yz plus the partial with respect to y of xyz squared plus the partial with respect to z of y over xz. Okay. Partial with respect to x here is just going to be e to the x times cosine of yz plus partial with respect to y here is xz squared, plus partial with respect to z, I can rewrite this piece as y over x times z to the negative 1. So that's going to give me a minus y over x z to the negative 2, and I'm just going to put that as a z squared on the bottom. So that's the real valued function I get by taking the divergence. Okay. Now, just like curl, the name divergence is kind of loaded. We will see that it has a physical interpretation as we get a little bit further along. Okay, so right now these definitions of curl and divergence these are sort of the plug and chug definitions. This is how you would calculate them. We're going to get equivalent definitions eventually that actually tell us what it means. Take this thing, this physical quantity, measure it, apply this limit to it, and you get this thing called divergence. Turns out it's equivalent to this plug and chug definition. Okay. We don't have enough background yet to be able to understand fully what it means, but I will tell you that yes, the reason it's called divergence is because it does have to do somehow with how things are diverging or going out, and we will eventually have the tools to understand that a little bit better. Okay. For right now, I want to just take a look at one quick theorem. Let's see, what is the theorem? Theorem 11. Theorem 11 says if f, which is just p, q, r, I'm going to omit writing p of xyz, q of xyz, r of xyz, but these are all real valued functions of three variables that are the components of this vector field in 3 space. If this is a vector field in 3 space, obviously, whose components have continuous second partials. So the components are just the 3 functions p, q, and r. We're going to require that their second partials be continuous. Then, if I take the divergence of the curl of f, I'm going to get 0. And that is 0 the number, not 0 the vector, because while curl of f is going to be a vector field, the divergence, remember, is a real valued function. Okay. So this is just the constant real valued function 0. Okay. The proof of this is just a lot of plug and chug calculations. Okay. So I'm going to work out what's the curl of f. Once I've done that, we'll take the divergence of it. So the curl of f is del crossed with f. So that's just my symbolic determinant, I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. Component functions p, q, and r. So, let's see. I'm going to get, if I look for the i's, I'm going to get the partial of r with respect to y minus the partial of q with respect to z. For the second component, remember to do it backwards, I'm getting the partial of p with respect to z minus the partial of r with respect to x. And for the third component, I'm going to be getting the partial of q with respect to x minus the partial of p with respect to y. Running out of space here. Okay, so now I want to try to take the divergence of that. So the divergence of the curl of f is going to be del dotted with the curl of f. And that's just the del operator dotted with this thing. So that's partial r partial y minus partial q partial z, comma, partial p partial z minus partial r partial x, comma, partial q partial x minus partial p partial y. So hopefully you see what's happening here. I'm going to now take another partial derivative of these things. So I'm going to be getting second partials of my component function. I'm starting to see how they might cancel out. Okay. So here I'm taking the partial with respect to x of these two things. So I'm going to get the partial squared r partial x partial y minus partial squared q partial x partial z. Now certainly nothing cancels there because they're different functions and different combination of variables. But I'm going to add to that, I'm going to take the partial with respect to y of these two. So I'm going to get partial squared p partial y partial z minus partial squared r partial y partial x. Plus, now I can add to that, I'm going to take the partial with respect to z of these guys. So I'll have partial squared q partial z partial x minus partial squared p partial z partial y. So let's take a look. This one had some r's in it, and that was the mixed second partial of r with respect to x and y. There's the other mixed second partial of r with respect to x and y, and this one's negative, so they're going to cancel each other out. Okay? Now, remember, we did suppose that the second partials of p, q, and r were continuous. If they're not continuous, we don't know that the mixed partials are equal, but since they are, they're equal. These guys cancel each other out. Now here, that was a mixed second partial of q with respect to x and z, and this one's negative. Here's a mixed second partial of q with respect to the same variables, x and z, but this one's positive. Those guys are equal. They cancel each other out. This is a mixed second partial of p with respect to y and z. This is the other mixed second partial of p with respect to y and z. This one's positive, this one's negative. Those guys cancel each other out, so we do in fact get 0. So the equality of mixed second partials is actually a really, really powerful tool, and it allows us to prove this, which I believe was theorem 11.